So the next one says to solve the following logarithmic equations, give an exact solution and an approximation to 4 decimal places as needed. So for the first one, I can see that this is log base 3 of 2x plus 5 equals 5x minus 13. So since we have the same log base 3, I can just set those two parts equal to one another. So 2x plus 5 equals 5x minus 13. I can subtract the 5x over. I get negative 3x is equal to negative 13 minus 5 would be negative 18. And then I can divide by negative 3. And I get 6. The only thing I need to check here is I need to check whether this x that I've got here works in my original equation. So if I plug in 6, I get log base 3 of 2 times 6 plus 5. That's a positive number. But when I plug in 6 here, I get 5 times 6, which is 30 minus 13, again, is positive. So this answer actually checks out. There are some times when you're solving these equations that you get values for x that don't work in the original equation because the domain restriction. So inside of a log function has to always be positive. Okay, so for the next one, we'll have to do a little bit of arrangement. So let's take a look at it. So for this one, I have log base 6 of 7x minus 2 equals 1 plus log base 6 of x plus 5. Okay, so what I'm going to do is I'm going to subtract the log base 6 of x plus 5 over. Okay, and then I'm going to use my laws of logarithms to combine that into one log. So that combines in the following way: log base 6, and since it's a subtraction, that's going to be division. 7x minus 2 over x plus 5 equals 1. Now I'm going to use my property of logarithm to rewrite that as an exponential function. So again, my base is 6, and I'm raising it to the power 1. So that says that 7x minus 2 over x plus 5 is equal to base 6 to the power 1, which is just 6, really. So now I can multiply the x plus 5 over, distribute the 6, subtract the 6x over, and add the 2. So I get x equals 32. Now I just need to check that that works in my original function. So I'm going to take this x equals 32, and I'm going to plug it back in. So 7 times 32 minus 2, that'll be positive. And then 32 plus 5 is going to be positive. So that works. So the correct answer is 32. Okay, so for the next one, we'll come over here and do it. So I have log base 2 of x equals 4 minus log base 2 of x plus x minus 6. Okay, and so I want to add that over. So I have log base 2 of x plus log base 2 of x minus 6 equals 4. And I can combine that into 1. It'll be a product of the inside part. So I have log base 2 of x times x minus 6 equals 4. Now I can rewrite that in terms of an exponential function. So I have x times x minus 6 is equal to 4 to the power, 2 is the base, excuse me. So 2 is the base and the power is 4. So 2 to the 4th. And then I know 2 to the 4th is 16. So I'll have x squared minus 6x, and then I can subtract the 16 over. And when I factor that, let's see, how does that factor? So x, and 16 is 2 times 8. So I think that'll get me the 6. 8 times 2, so I want the 8 to be negative and the 2 to be positive, and that will give me the minus 6 in the middle. And so that gives me x equals 8 and x equals minus 2. And so now I want to take those two answers and plug them back into my original function up here. So if I plug in 8 minus 6, that's positive inside, log base 2 of 8, that works out. But when I plug in negative 2, I get a negative answer here and a negative answer here on the inside of that log. We can't have a negative number inside of the log. It's not defined there. So the only answer that works is 8. Okay, so the next one says solve for the indicated variable. So I want to solve that thing for t. Okay, so one thing I want to notice about this is I want to look at where that t occurs. Now the thing I'm solving for is up there in the exponent, and so what that means is I'm going to need to use logarithms to be able to knock that t down to the same level as the base. So I can take the log of both, the natural log of both sides, p times 1 plus r over n to the nt. Now this I can see is a product of two things, so I can split that product up. You might be tempted to take that nt out front, but you have to notice that the nt is not a power of this p, right? So I actually have to break it up as a product first, and then I can knock that power down. So I get natural log of a equals natural log of p plus natural log of 1 plus r over n, the whole thing raised to the nt. And since all of that is raised to the nt, now I can knock that power down using the rules of logarithms. So I'm going to get natural log of a equals natural log of p plus nt natural log of 1 plus r over n. Okay, and now remember, I'm solving for this t right here. And I can see that t, so I have some stuff here that doesn't have a t in it, so I can subtract that over. And so I get natural log a minus natural log of p, which I can combine into one natural log if I want. And that's equal to nt natural log of 1 plus r over n. So then the thing I'm solving for, this t here, oh, sorry, I erased it. I meant to highlight it. This t here has things that are multiplied by it, so I can divide those things over to undo that, and then I'll have the t by itself. So I'm going to get n is equal to, when I divide that stuff over, I'm going to get t is equal to natural log of a minus natural log of p divided by n natural log of 1 plus r over n. So I can do it that way. And again, like I said, that natural log a minus natural log p, that could be combined into one natural log of a over p. Okay, so for the next one, I want to solve that for b. So notice where that b is. It's stuck inside of that log. So what that means is I'm going to need to take things to the 10th power to be able to solve for that. So let's get the b, the term that has the b in it by itself. So I'm going to get log of b is equal to 2.3 m minus or plus 1.7. And so now I'm going to rewrite that in terms of an exponential function. Remember, this log is base 10. I'm just going to write the 10 down there so we can see it. So that's telling us that b is equal to, the base is 10, the power is this 2.3 m plus 1.7. So that's the solution there to part B. Next one, Matilda and Horace open a retirement account with $120,000. How many years will it take for the money to grow to $800,000 if it grows at a rate of 4.5% compounded monthly? Okay, so what we want to do is we want to figure out how many years it will take. So I know the model that I want to use is P is equal to P naught times 1 plus R over N to the NT, where R is the rate written as a decimal, N is the number of times it's compounded per year. And P naught is the initial amount. T, again, is the number of years, and P is the amount in the account after T years. Okay, so what I want to do is I want to solve for how many years it will take for this to happen. So my initial amount is 120,000. You know what? I'm just going to write it as 120 and know that it's, well, okay, I'll write 120,000. I was going to say know that that's in thousands, but that's fine. Okay, 1 plus, my rate is 4.5%, so I have to write that as a decimal, 0.045. If you ever don't know what to do with that, remember percent means out of 100. So you can type into your calculator 4.5 out of 100, so divided by 100, and that will give you the decimal approximation for that. Over, it's monthly rate, so that's going to be 12 times per year it's compounded. And then I get 12t equals the amount I'm looking for, which is $800,000. Okay, and so then I just want to solve that for t. So first I can start by dividing the 120,000 over. So if I do 800,000, oh gosh, how many zeros do I need? 1, 2, 3, 4, 5. Divide it by 120,000. I get 20/3 equals, and then I have 1 plus 0.045 over 12 to the 12t. Now I can take the natural log of both sides if I want to. Natural log of 20 over 3 is equal to the natural log of that thing. And why am I doing that? I'm doing that because the variable I'm trying to solve for is up in the exponent. So I'm going to have to use natural logs to knock it down. Okay, so that means that 12t can pull out front. And then I can divide that stuff over. So I'm going to get t is equal to natural log of 20/3 over 12 natural log of 1 plus 0.045 over 12. And I can plug all of that into my calculator. So natural log of 20/3 divided by, and then I'm going to have to put parentheses here around the bottom. 12 natural log of 1 plus 0.045 over 12. And that gives me 42.2. So it says round to the nearest year, so 42 years. Okay, and what you might notice is that's really similar. What we just did here is similar to what we did here in part A. So the same work that we did, the same steps that we did, we had done those in general in part A of number 50. So the next one says the population of a rural community in 2035 was 3,050 in 2010. The population had increased to 3,500 in 2015. Assuming exponential growth, find the following: the growth rate to 4 decimal places as a percentage, and estimate the population in 2022 if the trend continues. Okay, so it says exponential growth, but it doesn't say whether it's continuous growth or compounded annually. I just did real quick, I did it both ways and saw that the way that they want you to do it is continuously, but it should say here compounded continuously. Okay, and so for this model, we're using P equals P naught e to the RT. So we can do the, so the initial amount was 3,050. The amount that I get in the end is, it's after 5 years. So T is going to be 5. So after 5 years, I get that. So we can divide that over. And then take the natural log of both sides. And then divide by 5. And so that gives us 0.0275. So that means R is equal to 2.75%. Then estimate the population in 2022. So again, remember T is the years since 2010. So that means that in 2022, that's going to be T is equal to 12 there. And so I can use my model with my new percentage that I got. And I can say P equals P naught, which is 3050, the population in 2010, E to the, my rate is 0.0275, and I want to do in 12 years past 2010. So that all goes up in the exponent. So I can plug that into my calculator. And that gives me P equals 4242.45. So 4,242. Okay, a sample found at a dig site was determined to have 68.78% of the C14 still remaining. Use the model to determine the age of the sample. Okay, so let's see here. So the initial amount we don't know, right? We don't know the initial amount, but we do know that it has 68% still remaining. So we can write it this way: Q equals Q naught E to the negative 0.000121 t. So I want to solve this for t is what I'm looking for. So I don't know how much I initially had, but I do know that after, I'm trying to find how many years. I had 68.78% left. So I could say Q naught, and then this is Q naught times 0.6878. E to the negative 0.000121 t. And so I can divide both sides by Q naught. So that's going to get rid of that Q naught. So 0.6878 is equal to E to the negative 0.000121 t. Now I can take the natural log of both sides. And since that negative 0.000121 is multiplied by the t, I can divide it over. And I get t is equal to the natural log of 0.6878 divided by negative 0.000121. And when I type that into my calculator, I get 3,093 years. So that sample is estimated to be 3,093 years old. Okay, and I think we're just rounding to the nearest year there. Okay, the last one on this page, the population of California can be approximated by the logistic growth function, and there's the function, where t is the number of years since 2000. Show all work. The first one is determine the population in the year 2000. So in the year 2000, since t is the number of years since 2000, that means in the year 2000, t would be equal to 0. So I want to plug in 0 for t and see what p of 0 is. So I get 95.2 divided by 1 plus 1.8, and then this is going to be end up being e to the 0. We know e to the 0 is 1, so I'm going to get 95.2 over 1 plus 1.8. So when I plug that into my calculator, 95.2 divided by 2.8, I get 34. So that tells me that the population of California in 2000 is 34, and it says this is measured in millions, so 34 million. Okay, and then determine the population of California in the year 2022. So in the year 2022, that will be when t equals 22. So I can plug that into my function. So I'm going to plug in 95.2 over, and I need big parentheses around the bottom here, 1 plus 1.8 e to the 22 times negative 0.0018. All right, that gives me 43.04. Okay. And then part C, use the model to determine when the population of California would reach 68 million. So I want to set 68 million equal to 95.2 over 1 plus 1.8 e to the negative 0.018 t. So I'm trying to solve for this t down here. I'm going to start by multiplying both sides by the denominator, and that'll clear out my denominators for me. So I'll get 68 times 1 plus 1.8 e to the negative 0.018 t equals 95.2. Now I can go ahead and divide that 68 over so I don't have to deal with it. So I have 1 plus 1.8 e to the negative 0.018 t. What does that divide it? If I divide 95.2 divided by 68, does that give me something nice? Oh, it's 1.4. Okay, I could set that equal to 1.4. Then I could subtract the 1 and divide by 1.8, and I'm going to get e to the negative 0.018 t is equal to, let's see, 1.4 minus 1, and all of that divided by 1.8. That gives me 2/9 when I write it as a fraction. As a decimal, that's 0.22222. So you can just hit math frac, and then it gives it to you as a fraction. Now I can take the natural log of both sides. Running out of space here. Okay. So if I take the natural log of both sides, I get negative 0.018 t is equal to the natural log of 2/9. And then I can divide by negative 0.018. So I get natural log of 2/9 divided by negative 0.018. And I can plug that into my calculator. And it gives me 83.559. How close do I need to be here? Round to the nearest year. So 84 years? And so that would be in the year 2084. What is the limiting value of the population of California under this model? So for these logistic type functions, the limiting value is always going to be this top number. So the limiting value is 95.2 million. Next page, the table gives the diameter of a sugar maple tree along with the corresponding age for 6 different trees. So this isn't the same tree. We're looking at sampling of 6 different trees, the age and their millimeters. So our input is the millimeters, and then the output is their age. So maybe I'm using the millimeter diameter to determine the age of the tree. So state which model best represents the data. So it might be a little bit hard for me to tell right now. I think what I'm going to do is use my calculator and try to plot these points and then see what I have. I cleared out my list 1 and my list 2, and I'm going to type them in. So I have 1, 50, 100, 200, 300, 400. And then I have 4, 60, 72, 82, 89, and 94. Okay, and I'm going to do, when I graph this, I'm going to go to my y equals, clear out anything that's there, turn on my plot 1, go to zoom. If I go to zoom stat, so if you go to the zoom button, go down to number 9, zoom stat, that will give you a window that has your stuff in it really nicely. Okay, so is it linear, exponential, logarithmic? It looks like, when I look at it in the calculator, it looks like this. And so that looks like a logarithmic function. So I'm going to say this is logarithmic. And so use the regression capabilities of your calculator to find the regression model. So I'm going to go to stat, calculate, and go down to I think LN regression. So if I hit that one, it's going to give me y equals a, let's see, round everything to 2 decimal places. So 3.3 plus b is 14.9 ln of x. Then it says, use the model to determine the age of sugar maple tree that has a diameter of 150 millimeters. So that would be y equals 3.3 plus 14.9 times the natural log of 150, which gives me 77.95. So 78 years old.